In modern data centers, between 25 and 60% of all CPU cycles are wasted, not on computation, but on waiting for memory. When a program reads data that isn't in cache, the CPU must fetch it all the way from DRAM. That round trip takes hundreds of nanoseconds, an eternity in CPU time. Hardware designers had a fix: simultaneous multithreading, or hyperthreading. Run a second thread on the same core to fill those idle cycles. But for latency-critical services, this backfires. The competing thread can increase response latency by up to 92 times. And there's no middle ground. Hyperthreading is all or nothing. MSH takes a fundamentally different approach. What if software could decide precisely when to switch away and when to come back? Think of it like a chef. When they put something in the oven, they don't just stand there staring at it. They start prepping the next dish. When the timer goes off, they switch back. MSH turns every cache miss into a scheduled context switch. Yield to a scavenger task while the data is fetched, then resume the primary task the instant it arrives. MSH works in two phases. First, an offline profiler identifies the exact load instructions that frequently cause cache misses. These are called delinquent loads. The binary is then instrumented. A prefetch instruction is inserted before each delinquent load, immediately followed by a yield to a lightweight coroutine called a scavenger. A key optimization reduces overhead. Instead of saving and restoring registers at every yield, MSH moves this to the loop boundary, so overhead is paid once per loop, not once per iteration. At runtime, the scheduler dynamically assigns scavengers to primary threads and can chain multiple scavengers when stalls are dense, scaling concurrency beyond what any hardware can do. The results are compelling. MSH achieves 72% of hyperthreading's throughput at latency levels where hyperthreading must be completely disabled. When scavengers are themselves memory-bound, MSH actually beats hyperthreading by 2 times because chaining multiple coroutines goes beyond hardware's 2-thread limit. MSH proves that software can harvest idle CPU cycles more efficiently than hardware, with fine-grained configurability and no source code changes required. In data centers where every CPU cycle is money, turning wasted stall time into useful work is a meaningful advance.